Well, hey everybody, this is Mr. Kenny here. So we're going to go over for the Matter and Measurements test review for the 2017 through 18 school year. This is part 2, the questions 15 through 26. So let's zoom out so we can see our page a little bit better. In the previous one, we went over all of those. Yay. Okay, so now we're going to turn this one over, and we got a few more conversions to do. You've got to convert 60 grams, so 60 grams G over 1. Remember, always put your givens over 1. And then the conversion factor, when you turn the page over, is that we've got, let's see, we don't have grams to kilograms, but look at here, right above this, you need to know that, okay, if we just change that 1,000 on this to grams, that would equal 1 kilogram. So you need to know that kilograms and all the units are interchangeable on there. So we're going to say that 1,000 grams is 1 kilogram. Those will cancel out, and we get 60 over 1,000. And when you punch that into your calculator, I think we're going to end up with 60 divided by 1,000 should be 0.06 kilometers. Now we want, wait a minute, sorry, kilograms, not kilometers. Sorry, my brain was somewhere else. There we go. Just change, there we go, kilograms. So we got 0.6 kilograms. Now, the next one says convert your answer into pounds. Okay, so 0.06 kilograms over 1, that becomes our given. And on the front, it says there is, I think there's a 1 kilogram is 2.2 pounds. So we want to set it up so kilograms are down there, so they'll cancel, and pounds are up here. And I believe it said 1 kilogram was 2.2 pounds. Cancel off the kilograms. And when we multiply 0.06 by 2.2, you should get 0.132. You need to be prepared on this test to round to 1 or 2 decimal places. So we've got 6 million milligrams, mg. Yikes, we want to go to kilograms. Well, first, this is a milligram. Let's convert it to grams, and then you can convert the grams to kilograms. So this will be a 2-step one. So the first thing is, when you look on your chart over there, it says that let's see, milligrams to kilograms. Let's see, where is that going to be? Well, you know, that's not on the given here. I hate it when we do that. But I'm just going to change this to 1,000 mg's, milligrams. That will equal 1 gram. And we'll have those actual numbers on the test for you. So I'm going to say 1,000 milligrams is 1 gram, because we need to set it up that way so that the milligrams cancel. And then we're going to change the grams into kilograms. And that one I think was given for us, that there's 1,000 grams in, we had it, I kind of rewrote that one right there in 1 kilogram. The grams cancel, the grams cancel. So now, wait, look at here. Those 3 zeros cancel with those 3 zeros cancel with those. The answer is 6 kilograms. How many pounds is this? That's our new given, 6 kilograms over 1. And over here it says that kilograms, 1 kilogram is 2.2 pounds. So we're going to say that 1 kilogram is 2.2 pounds. That was, we had that up in the similar one up there. So let's see, 6 times 2.2, it's going to be around 13, I think. 6 times 2.2 equals 13.2 pounds. Okay, if you are 15 inches tall, how much is this in centimeters? So, excuse me, 51 inches over 1. We have a conversion factor over there that changes, I think we have inches to centimeters right there, so 2.54 centimeters in 1 inch. So we're going to say we want inches and centimeters. 2.54 centimeters is 1 inch. The inches cancel out. And so it's going to be 2 times 51, so the answer is going to be somewhere around 103, I'm going to guess. So let's see, 51 times 2.5, oh, 2.54. It may be a little bit higher than 129.54 centimeters. Oh, really? We're doing this? How tall is that in millimeters? You know, if you work these out, we're going to put the given over 1. Oh, and that is centimeters. And we're going to say, okay, so now we have 100 centimeters in 1 meter. These cancel out. And then, let me fix that there a little bit. And 1 meter has 1,000 millimeters in it. Okay, so what's going to happen here is, now those 2 zeros will cancel off 2 of those, and it becomes this number times 10, which will be 1,295.4 millimeters. How many milliliters are in a 60-ounce soda? 60 ounces is our given over 1. We've got a conversion right here that says 1 ounce is 29.57 milliliters. So let's see. 1 ounce is 29.57 milliliters. And the reason I knew to set it up, oh, that's 1 ounce down there. Sorry, I would put that in. The reason I know that this is 1 ounce goes here, we want to set it up so those will cancel. So 60, punching this in the calculator, 60 times 29.57 equals, I want to double check, I didn't trust my times 29.57. It's going to equal 1,774.2 milliliters. Soda good for you? No. Okay, going on. All right, I went over this in every one of my classes. I do not want to go over it again because I've done it now today and yesterday quite a few times. So what I'm going to do, I'm going to cheat right here. I'm going to just put in what we did in class. Now don't freak out. First off, when you read the problem here, let me see, are we on the right one here? Yeah. Set this up, and I gave you a hint. We're telling you it's 10 minutes to walk 1.5 kilometers, so you set it up like a fraction. Now the problem wants to know how fast is this in kilometers per minute. Kilometers per minute is the reciprocal of this, so you just turn it over like this to 1.5 kilometers per minute. So we have this set up. So in the calculator you punch that in and we end up with 0.15. Now the next question is, how fast is that in kilometers per hour? So now we're taking our given over here, 0.15 kilometers per minute, and then we just want to use the conversion factor that there's 60 minutes in 1 hour. That'll cancel out the minutes, and we get 9 kilometers per hour. Now the next question wants us to change this one. This becomes the given over here. How fast is this going to be in miles per hour? So we're going to change the kilometers to miles, and when you look on there, there's 1.61 kilometers in 1 mile. So these cancel out, and we end up getting 5.6 miles per hour. We're kind of used to that. Now, on the test, we're likely to give you a problem more like this. We're going to give you maybe 5.6 miles per hour, this given, and we might ask you to convert it into feet per second. Now we goofed up. We didn't put the conversion factor for feet to miles. Sorry, you can look that up on your phone. It turns out to be 5,280 feet is 1 mile. That allows us to cancel this. Now we need to get the hour converted into seconds. So now over here, 1 hour is 60 minutes. That lets us cancel here. Now we want to get rid of the minutes. So we're going to say that 1 minute is 60 seconds. And when you work it all out, 5.6 times 5,280 divided by 60 equals 8.2 feet per second. Number 20. It says 2 boxes the same size. Okay, 2 boxes the same size. I did my best. They have a density of 5 grams per cubic centimeter and 10 grams per cubic centimeter. Okay, so let's just say for fun, okay, so they got that density, okay. I'm just going to pretend, hey, what if, I'm just going to pretend these are cubic, okay. Which box would be heavier to lift? Which box has more stuff in it? Draw a model of both. Well, look at, this one has 10 grams for every centimeter cubed, excuse me. So I'm just going to assume, let's say these boxes we drew, they're exactly 1 cubic centimeter. I'm going to put 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, say each of those is a gram in there. This one only has 5. So this one will be heavier, heavy, I-E-R, misspelled heavier, H-E-A-V-I-E-R. This one will be heavier, okay. Which has more stuff in it? Okay, the one with the higher density always has more stuff in it. Higher density has more stuff in it if we have the same volumes. And I drew a model of the boxes. What is the law of conservation of matter? Cannot create nor destroy matter. D-E-S-T-R. Maybe rewrite that. You cannot create or destroy matter. And we figured that out when Anton Lavoisier, among others, did experiments in a closed system. They had to get a jar and close the jar and then burn their stuff or do their reactions. And how does it relate to products in a chemical reaction? So after they sealed off these containers, they found out that if you say started with a piece of wood in here, okay, you had a piece of wood and you heated it up over a fire, keeping this sealed, when you were done, they found, okay, you had a little bit of ashes here, but all over the place there was a whole bunch of H2O and there was some CO2 jammed in here under high pressure, but the weight stayed the same, the mass stayed the same. So when this happened, same mass, they realized that that you were not creating or destroying matter. And if you were to unscrew this top, you would have a bunch of gases go and fly out. Open and closed chemical system. Okay, a closed system. Okay, the chemicals are trapped inside. They cannot go in or out. It's a sealed jar. This one right here, without a lid on it, the chemicals can go in and out. So this is open, this is closed. Chemical system, we're talking about chemicals here. In both of these, heat can go in and out, no matter what. But if we're talking closed, if we're talking chemical systems, there we go. What is kinetic energy? Motion in atoms. Draw and explain the kinetic energy of atoms in a solid, liquid, and a vapor. We did that in class. We said, okay, in a solid, they're really close together and they're super organized. They're in, they're lined up. They're in a crystal. They can vibrate a little bit, but they can't move. In a gas, they're going to be really close to each other still, but they're not going to be locked in a certain pattern, and they can move quite a bit. These guys can just barely move a little bit. They vibrate. In a liquid, they can move a little more. In a gas, they're going to be far apart, and they are moving fast. They move really fast. So this would be a gas, liquid, and the kinetic energy here is low. Kinetic energy is high, which means they're moving really fast, and because they move really fast, they're going to take up more room. And label the triangle with the change of state. Okay, let's see. So I'm just going to make this easy. If we just make this H2O, let's make this ice, let's make this steam. Then it's a little easier for us. So if water changes to ice, we call this one freeze. If ice melts into water, we call that melting. If water changes into a vapor, we call that vaporize, or changes into a gas, vaporize. If steam changes into a water, we call that condense. That happens all the time in my classroom. When you all, half of you, when you bring your water bottles in my room, you leave and you leave a little ring of condensed water. That's kind of cool. Now, when a steam changes directly to ice, that's called deposition or deposit, D-E-P-O. And that's going to happen like that's frost in the morning, or freezer ice, if you really would like freezer ice happens. When you open up your freezer, water vapor instantly freezes. The other way around, when like if you've ever played with dry ice, when it goes from the solid to the vapor, that's called sublimate. Label the triangle. Oh, we already did that. Yay, did that. Good. List each state of matter and their kinetic energy, their motion. Well, I did it right here. Okay, a solid. I'm going to come right back up to this one. So we have a solid right here, and its kinetic energy is low because the particles can only vibrate. Over here, a gas, the kinetic energy is high because they are moving really, really fast, and that makes them spread apart, and it makes gases have more energy inside of them, kinetic energy, and they tend to take up more spaces, and liquid's going to be in between. It can move, so it's got a medium kinetic energy, and that is motion of particles. And let's see, draw a diagram showing how atoms move in each state. How atoms move in each state of matter. Okay, I'm going to draw these guys in a solid. They're like really close to each other. They're just kind of vibrating. In a liquid, they're still really close to each other. They can freely move. But I'm going to draw medium arrows. Okay, so they can kind of move around. They can move around, but they're still really close together. And in a gas, also known as a vapor, those 6 particles are moving really fast, and they're going to do their best to stay away from each other. So they're going to be 1, 2, 3, 4, 5. We'll put another one here. So they're spread out quite a bit, but they've got quite a bit of speed. All right, so ladies and gentlemen, there you go. Powering down. Let's see, powering down. Goodbye.